When we're calculating bending stresses, one important step is to be able to calculate the moment of inertia of the cross-section that we're looking at. For simple shapes, of course, the moment of inertia is tabulated. For example, for a rectangle, the moment of inertia about an axis passing through the center, or the centroid, is 1/12 base times the height cubed. Now, if we're looking for the moment of inertia about another axis, as long as that axis is parallel to the centroidal axis, we can use the parallel axis theorem. So, to find the moment of inertia about the axis that's labeled x prime here, we would take the 1/12 bh cubed and add to that the area of the rectangle times d squared, where d is the distance between the two axes. Now, we'll use this to be able to find the moment of inertia of a compound area. So a compound area is simply one that's made up of several simple shapes, and a lot of times in structural analysis, most commonly it's going to be made up of a series of rectangles. So the examples we're going to show are compound areas made up only of rectangles, such as this T-beam that's shown here. Now again, to do bending calculations on a cross-section like this, we need to know the moment of inertia about the centroidal axis, that is, passing through the centroid of the section, because that is the neutral axis of bending. So the first step is going to be to locate where that axis is. In other words, where is the centroid of the cross-section? Once we know that, we can look at each of our rectangular regions, and we can find the moment of inertia about that centroidal axis using the parallel axis theorem. And then we sum those values together. That will give us the moment of inertia of the entire cross-section. So here's a simple example. We're going to look at a T-beam that's made up of two 6-inch by 1-inch rectangular members. So the first step is that we need to locate where the centroid is. And so we need to have some datum, I usually pick the bottom of the section. You can certainly do it from the top of the section if you prefer, but as long as you're consistent. What we're really doing is taking a weighted average of the area times y bar. So we'll find the area of each segment, its centroid location relative to our datum, and take the product of those, add them together, and divide by the total area. So in this case, both of our areas are 6 square inches. For the web, which we called area 1, excuse me, for the flange rather, the distance from the bottom of the section up to its centroid is 6 inches plus half of the thickness of the flange, or 6.5 inches. For the web, the distance from the bottom of the section to its centroid is half of the web height, or 3 inches. So for each row there, we multiply the area times y bar, and then we sum those values as well as summing the total area. And so the y bar of the section is the sum of the area times y bars, the 57 cubic inches, divided by the total area, 12 square inches, and so the centroid is located at 4 3/4 inches above the bottom of the section. So now that we know that, we can add a couple of columns to our table here, and so we're looking at the flange first. So the moment of inertia about its own centroidal axis is 1/12 base height cubed. In this case, it's 1/2 inches to the fourth. D, the distance between the axis passing through the centroid of the entire cross-section and the axis passing through the centroid of the rectangle, in this case is our y bar value of the individual segment, which was 6.5, minus y bar of the entire section, which is 4.75, so that difference is 1.75 inches. And so now the moment of inertia of that rectangle about the centroidal axis is 1/12 bh cubed plus ad squared, and that gives us a total of 18.875 inches to the fourth. So we'll add those numbers to our table. Now we move to the web, and the moment of inertia about its own centroidal axis, 1/12 bh cubed. Of course, the base in this case is 1 and the height is 6, so that comes out to be 18 inches to the fourth. The distance between the two axes, again, we're just taking the number out of the table, the y bar value of that particular segment, minus the y bar of the entire segment. Of course, you can switch those around if you want, because that value gets squared, so it doesn't matter if it's positive or negative. And so the moment of inertia about the x-axis here is turns out to be 36.375 inches to the fourth. And so in this case, the contribution to the moment of inertia of the web is actually greater than that of the flange. We add the two together, and that's our answer. The moment of inertia is 55.25 inches to the fourth. Now, if we put another 6x1 piece on the bottom of this to make an I-beam or a wide flange beam, and we want to find the moment of inertia, well, we can do that a little bit differently this time. First of all, because we're symmetric from top to bottom, we know where the centroid is. We don't want to waste any time calculating that. The centroid is halfway between the top and the bottom. And instead of looking at the two flanges separately and the web separately, in other words, dividing it up into three pieces like that, instead we can take the entire rectangle, as though this were a total solid cross-section, and subtract off these two pieces. And the advantage of doing it this way is that all of these segments have centroids that lie along the x-axis, so we don't have to use the parallel axis theorem at all to do this. And so our calculations will go like this: for the solid section, 1/12 bh cubed is b would be 6 inches, and the overall height is 8 inches. And for the segments that we're going to remove, of course being two of them, each of the base, since the overall base is 6 inches and the thickness of the web is 1 inch, that leaves us 2.5 inches on each side. And so we can do that calculation and find the moment of inertia as 166 inches to the fourth. Now, if we did this by the other method, in other words, our first method, by dividing it up into three regions, we do get a little more insight into the problem, perhaps. When we look at each of the flanges, we see that the 1/12 bh cubed term is very small, but the AD squared term is quite large. And of course, the two flanges, those values are exactly the same. If we look at the web, the 1/12 bh cubed, of course, is relatively large because of its height there being cubed, and it lies right on the x-axis at centroid, so the AD squared term is 0. And again, when we add everything together, we get 166 inches to the fourth, so the same result. But what you can see is that most of the value of this, you can see the 74 and 74, most of the contribution is from the flanges. And most of the contribution of the flanges is due to the AD squared term. In other words, it's the most efficient way to build a beam, which explains why wide flange beams are used a lot, is to get the material as far away from the neutral axis as possible. And so with that in mind, how would we stiffen this beam if we needed to increase the moment of inertia? What's the most efficient way to do that? So we've looked at a couple of alternatives, each of which adds 1 square inch to the total cross-sectional area. Well, the most efficient way, as we just talked about, would be to increase the overall height of the beam. So if we increase the web height from 6 inches to 7, we find the moment of inertia increases by about 33%. And remember, adding 1 square inch just takes us from 18 to 19 square inches. So we increase the area or the weight of the beam by about 5.5%, but increasing the height increases our moment of inertia a good bit more than that. Now, a lot of times you can't do that, though, because you might be restricted on how tall this beam can be. So another way of doing it would be to increase the flange width without increasing the overall height. And if you do that, the increase is much less. You could also increase the flange thickness, but again, if you have to do that without changing the overall height of the beam, you'll find the increase is only about 5%, so really on the same order that you're increasing the area by. And finally, the least efficient way is to increase the web thickness. So the web, of course, has to be there. You have to have a minimum thickness to be able to transfer the shear forces and also to prevent buckling on the portion of it that's in compression, but it doesn't add a whole lot to the overall beam stiffness. Now, one other thing I might point out, though, is that if you have a real complicated shape, for example, in this case, this is a type of aluminum extrusion that's used a whole lot in quick construction, then rather than doing this by hand, you can use the tools that you have available, and most CAD programs will be able to calculate the moment of inertia for you. In this case, in SolidWorks, I can simply click on this cross section, go to Tools and Section Properties, and what it will give me are the moments of inertia here as well as the cross-sectional area.